An endless void containing hundreds of world-ending phenomena. I mean, at least we think. A lot of what we know about space is theoretical and circumstantial, which leaves a lot to the anxious imagination of curious craniums like ours. Hi, I'm V, and these are 5 terrifying deep space entities that astronomers fear. Number 5. Pulsar. Pulsars are highly dense, rotating neutron stars that emit beams of electromagnetic radiation along their magnetic poles. These celestial objects were first discovered in 1969. Pulsars form through the gravitational collapse of massive stars during a supernova explosion. The core that remains after the explosion, composed mainly of neutrons, becomes extremely dense. Pulsars typically have a mass greater than that of the sun, but are compressed into a radius of only a few kilometers, so they're like really heavy but very small. Think like a shrink ray that decreases the space between atoms. The mass stays the same, but the area decreases dramatically. Pulsars exhibit rapid rotation, spinning several times per second. This rotation is a consequence of the conservation of angular momentum during the star's collapse. As they rotate, pulsars emit beams of electromagnetic radiation that are observable when these beams sweep across the Earth, leading to periodic pulses of radiation. The pulse periods of pulsars can range from milliseconds to seconds. The rotational stability is astonishing, with pulsars rivaling the rotational precision of our best atomic clocks. This regularity in their pulses makes pulsars invaluable tools for various astrophysical studies. They are definitely worth studying from a distance, because radiation. Pulsars exhibit extremely strong magnetic fields, billions of times stronger than Earth's magnetic field. Interaction of these powerful magnetic fields with the pulsar's rotation generates intense electromagnetic radiation. Pulsars are detected through radio telescopes, which capture the periodic bursts of radiation. Since their discovery, pulsars have been observed across various wavelengths, including visible, X-ray, and gamma-ray frequencies, providing valuable insights into their properties and environments. I often have to remind myself that gamma rays are a real thing and not made up. I watch too many movies. Some pulsars exist in binary systems where they orbit around a companion star, like they have a friend they really like to hang out with. The gravitational interaction in these systems can have profound effects, leading to changes in the pulsar's rotation rate and offering a unique opportunity to test theories of general relativity and influence. The precision of pulsar timing has potential practical applications, particularly in space navigation. Pulsar-based navigation systems can provide spacecraft with highly accurate position information, aiding in interplanetary and interstellar exploration. Number 4. Time dilation. Time dilation is a phenomenon predicted by Einstein's theory of relativity, where time appears to pass differently for observers in different gravitational fields or relative motion. In the context of space, time dilation becomes a crucial factor, impacting our understanding of time and its measurement in extreme out-of-this-world conditions. Gravitational time dilation occurs in regions of varying gravitational fields. According to general relativity, time flows more slowly in stronger gravitational fields. This means that clocks in stronger gravitational fields tick more slowly than those in weaker fields. Near massive celestial bodies like planets, stars, or black holes, the gravitational force is stronger, causing time to dilate. This effect has been experimentally confirmed through precise measurements of time on Earth and in satellites. Special relativity introduces another form of time dilation related to velocity. As an object approaches the speed of light, time dilation becomes increasingly significant. This effect is particularly relevant for objects traveling at a substantial fraction of the speed of light. The faster an object moves relative to an observer, the slower time appears to pass for that object. This phenomenon has been demonstrated in particle accelerators, where subatomic particles accelerated to high velocities exhibit longer lifetimes than their stationary counterparts. In space, both gravitational and velocity-related time dilation can coexist. For instance, an astronaut on a fast-moving spacecraft near a massive celestial body would experience a combination of these effects. The interplay between velocity and gravitational fields creates a complex temporal landscape. Think of Interstellar, which honestly doesn't really simplify this much, but maybe it'll help someone. GPS provides a practical example of this interplay. GPS satellites moving at speeds and experiencing weaker gravitational fields in orbit must account for both forms of time dilation to provide accurate location information on Earth. So why is it feared? Time dilation has practical implications for space exploration. As spacecraft travel at significant fractions of the speed of light, the onboard clocks would run slower relative to Earthbound clocks. This means that astronauts on space missions would experience less passage of time compared to people on Earth. Not drastically, it would be fractions of seconds at most. While the effect is subtle for current space travel speeds, as technology advances and humans consider interstellar travel, time dilation becomes a factor that must be carefully accounted for in mission planning. Number 3. Blitzars, short for Blitzar bursts, are cosmic events that have intrigued astronomers and astrophysicists. These phenomena represent a unique and intense burst of radio waves originating from deep space, leaving scientists to unravel their mysterious origins. Blitzars are believed to arise from the collapse of massive stars, culminating in the formation of highly magnetized neutron stars, or magnetars. When these magnetars undergo a rapid spin, their intense magnetic fields become distorted, giving rise to a colossal burst of energy in the form of radio waves. These energetic releases can outshine entire galaxies for brief moments. Blitzars are characterized by their extremely short durations, typically lasting only a fraction of a second. This brief but intense burst of energy distinguishes them from other astronomical phenomena, such as pulsars. The energy emitted during a Blitzar event is staggering, often exceeding the total energy output of our sun over its entire lifetime. Our sun's entire lifetime, please let that sink in. This makes Blitzars one of the most energetic events in the cosmos. Blitzars emit primarily in the radio wave part of electromagnetic spectrum. This preference for radio frequencies is a key identifier for astronomers studying these phenomena, allowing them to differentiate blitzars from other similar events. Detecting blitzars relies heavily on advanced radio telescopes equipped to capture and analyze radio wave signals. Blitzars share similarities with other cosmic phenomena known as fast radio bursts, or FRBs. While there is ongoing debate about their relationship, some scientists hypothesize that blitzars might represent a subset of FRBs, linking these two phenomena into the same category. The study of blitzars provides a unique window into the extreme physics at play within the densest regions of the universe. Understanding the mechanisms driving blitzar events can offer insights into the behavior of matter under the most extreme conditions. Blitzars, with their precisely timed bursts, have the potential to serve as cosmic chronometers. The regularity of their events, once fully understood, can contribute to the refining of our understanding of cosmic distances and the overall expansion rate of the universe. As radio telescopes continue to advance, providing more detailed observations, the mysteries of blitzars may gradually unfold, unraveling the secrets hidden within the realms of our vast and terrifying universe. Number 2. Quasars and Blazars. Quasars, short for quasi-stellar radio sources, are luminous, energetic astronomical objects. They represent the active cores of distant galaxies, harboring supermassive black holes at their centers. These black holes, with masses millions to billions of times that of our sun, accrete massive amounts of matter, releasing intense radiation across the electromagnetic spectrum. Quasars emit radiation across a broad spectrum, from radio waves to X-rays. Their emission lines, characterized by highly ionized atoms, facilitate their identification. The redshift of these lines, caused by the expansion of the universe, enables astronomers to estimate the quasars' distance and gauge the era in which they thrived. Functioning as cosmic lighthouses, quasars provide valuable insights into the early universe. Their extreme brightness allows astronomers to observe them from immense distances, offering glimpses into the conditions and processes prevalent in the cosmos billions of years ago. Blazars, a subcategory of quasars, are characterized by their intense variability and strong radio emissions. What sets blazars apart is their orientation of their jets, streams of particles ejected from the vicinity of the supermassive black hole. These jets are oriented along our line of sight, resulting in enhanced brightness and variability as relativistic effects amplify the emitted radiation. Blazars are prolific emitters of gamma rays, which again are real things and the most energetic form of electromagnetic radiation. This makes them objects of study for researchers investigating high-energy astrophysics. The extreme conditions near the black hole and within the jets provide unique laboratories for testing theories related to particle acceleration and magnetic field dynamics. The emission from blazars is dominated by synchrotron radiation, a process where charged particles spiral along magnetic field lines. This radiation spans the entire electromagnetic spectrum, from radio waves to gamma rays. blazars. Observing blazars across multiple wavelengths is crucial for comprehensive understanding of their physics. Quasars and blazars stand as fascinating celestial phenomena, each offering a unique window into the universe's intricacies. Quasars, with their distinct brilliance, serve as beacons from the early cosmos, aiding astronomers in unraveling the mysteries of our cosmic origins. On the other hand, blazars, with their peculiar jet orientations and high energy emissions, provide a closer look at the extreme astrophysical processes occurring near supermassive black holes. Number 1. Magnetars. Magnetars are one of the most powerful entities in the cosmos, distinct by their intense magnetic fields and formidable energetic output. These exotic celestial bodies, born from the remnants of massive stars, exhibit magnetic fields trillions of times stronger than Earth's, leading to astonishing astrophysical phenomena. Magnetars typically originate from the remnants of massive stars that have undergone a supernova explosion. As the stellar core collapses, it gives rise to a neutron star, an incredibly dense object composed mostly of neutrons. In certain cases, a subset of neutron stars evolves into magnetars due to a unique combination of factors during the collapse. What sets magnetars apart is their exceptionally strong magnetic fields, reaching strengths on the order of 10 to the power of 15 to 10 to the power of 17 Gauss, orders of magnitude greater than other neutron stars. Gauss is a unit of measurement for magnetic fields. I would try to further explain it, but it's just one of those things where the further you go into it, the more separate terms you have to explain, and then we would be here forever. These extreme magnetic fields exert immense forces on the surrounding environment, influencing nearby matter and generating intense electromagnetic radiation. Magnetars are X-ray emitters. The magnetic forces cause the acceleration of charged particles, leading to the production of intense X-ray radiation. Observations of magnetars often involve space-based X-ray telescopes to capture the X-ray emissions that reveal the magnetar's presence. One of the most captivating phenomena associated with magnetars is giant flares. These events release an extraordinary amount of energy in the form of X-rays and gamma rays, in some cases temporarily outshining the entire Milky Way galaxy. Giant flares are believed to result from the rearrangement of the magnetar's ultra-strong magnetic field, leading to a seriously catastrophic release of energy. Magnetars are also known for their experiencing starquakes, a seismic-like activity within their solid crusts. The intense magnetic forces can cause the crust to crack and release large bursts of radiation. These quakes are observed as pulsations from the X-ray emission from the magnetar. The colossal magnetic fields of magnetars have huge impacts on the surrounding space. They influence the behavior of nearby matter, creating intricate magnetospheric structures and impacting the evolution of neighboring celestial bodies. Understanding these interactions contributes to our broader comprehension of the dynamic processes shaping our universe. So you may be wondering, why is this thing number 1? Well, you know all the stuff we just went over about bursts of huge amounts of radiation and magnetic pulses? If no, go back to the beginning of this point. You should really be paying attention. As magnetar's magnetic field can become so strong that getting closer than 620 miles will dissolve atoms. Dissolving atoms! You know how insane that is? Do you know the theorized impacts that dissolving atoms would have on its own? This one is absolutely crazy, insane, and so flipping cool. And that brings our list to a close. Which of these deep space entities do you find the most fascinating? Let me know. I love hearing from you guys. Thank you so much for hanging out with me. I hope you enjoyed my nerding rambling, and of course, I hope you learned something. Keep it curious. Bye!